In this video, we are continuing our midterm review by focusing on the area between curves. So I want to look at this example where it says, let R be the region bounded by y equals x squared, x plus y equals 6, and y equals 1 that's entirely in quadrant 1. So as a brief review, the quadrants, remember, are the first quadrant is up here, the top right. Second quadrant is top left, and then it keeps going like that. This is quadrant 3, and that's quadrant 4. So I want to give you all the opportunity to just get this one started by first drawing a picture of this. So pause the video for just 1 to 2 minutes first to see if you can draw a picture of what this region looks like. So 4, 3, 2, 1, pause that video. Pause it for 1 to 2 minutes to see if you can draw a picture first. Alright, so hopefully you did that. Hopefully you paused it for about a minute or two to try drawing this picture. So let's talk about it. So I'm going to draw some axes, and let's draw y equals x squared. So I know that that is a parabola with a vertex at the origin, and it's facing upwards like this. And then, so that is, let's label it. That's y equals x squared. With x plus y equals 6, it's going to be helpful to isolate y, so I can see the slope and the y-intercept. Y equals negative x plus 6. So I can see that with that line, the y-intercept should be up here at positive 6. The slope is negative 1, so it's downward sloping. So my line looks something like this, and it would continue in that direction. So at some point it looks like this line and this parabola over here are going to intersect somewhere. So, okay, there's one more line, whoops. So there's also y equals 1. So let's draw that in. So y equals 1 is a horizontal line that goes through 1 on the y-axis. So 1. Okay, so that is y equals 1. So in this picture, there are two different regions that are bounded by these curves. So one of the regions is this part right here. I'm going to trace it out. This whole thing that I'm tracing out in blue, that whole part. And that part of the graph is part of it's in quadrant 1, part of it's in quadrant 2. But there's one other part of the graph that's bounded by these curves, and that is over here. That's this part of the graph that's bounded by those 3. And this pink part of the graph that I just drew, that is entirely in quadrant 1. So it's talking about that part. Alrighty. So now I want you to pause the video one more time to try finding the area of that region. So take 2 minutes to try this. It's not going to be enough time to finish the question, but the important part is, what are the key ideas? Thinking about how we'd begin and what those steps are. 4, 3, 2, 1. Pause that video. Pause it for 2 minutes to really give yourself a chance to think through, how do we begin? What are the main steps? Alright, so hopefully you paused it for about 2 minutes. And let's talk about it together now. So we need to begin by finding the intersection points. Okay, so I'm going to try to figure out where this parabola and that slanted line intersect. So to do that, I know what y equals for both of them. In the parabola, y equals x squared. And in the line, y is negative x plus 6. So I should be able to set those two y values equal. Okay, and I can rearrange this, move everything over to one side. So I get x squared plus x minus 6 equals 0. And now I can factor. So this factors nicely as x plus 3 times x minus 2. So I know that either x equals 3 or x equals, negative 3, my mistake. Let me give myself some more space there. X equals negative 3 or positive 2. So let's find the y values for each of these to really just be thorough. So for x equals negative 3, let's see, I could either plug it into the line equation, y equals negative x plus 6, or I could plug it into the parabola equation, y equals x squared, because it's supposed to be an intersection point. So that means it should be on both of them. So if I do it in the parabola equation, we'll get y equals -3 quantity squared, which is 9. And if I plug 2 in, we get y equals the quantity 2 squared, which is 4. So by looking at my graph, I can see that this intersection point over here is 2, 4. The -3, 9 is the other point where the parabola and the line meet. But I didn't care about that. That's part of the other region that wasn't entirely in quadrant 1. So we're not going to care about that other intersection point. So I also need to find this intersection point, so where the slanted line meets y equals 1. So I know the y coordinate at this point should be y equals 1. And to find the x coordinate, let's plug y equals 1 in to the equation of the slanted line. So that'll give me y is 1, 1 equals -x plus 6. So I'm basically plugging the 1 in for the y. And if I rearrange this, I get x on the left and 5 on the right. So that intersection point is 5, 1. I also need to know this intersection point here. And for that one as well, I know y equals 1. And if I plug that into the parabola equation, we get 1 equals x squared. And square rooting this, we'd get we'd get plus or minus 1 equals x. But we only care about x being positive 1. So we just want x to be equal to positive 1, because this intersection point has a positive x coordinate. So that intersection point is 1, 1. The other intersection point was over here. This one is -1, 1, which we don't care about for our region. Alrighty, so we got all the intersection points. We are ready to now set up an integral for this area. So I'm going to do this in 2 ways. So I'll call this solution 1 first. Solution 1, let's do this as a dx integral. So as a dx integral. So let me zoom this out a little bit so we can see the picture. So when we do a dx integral, we'll have an area from some number to some number. And we integrate the top function, y top, minus the bottom function, y bottom, dx. So on this interval, my x values start at x is 1 and go until x is 5. But on the interval, the top function changes. The top function changes when I reach 2, 4. So what that means is I sort of have to split this up into 2 regions right at that intersection point. And on the left, there's one top curve. It's the parabola. And on the right of that intersection point, there's a different top curve. It's the slanted line. Okay, so I'm going to need 2 integrals. The first one goes from where x is 1 to where x is at the intersection point. That's 2. Okay, and I'll have something dx. And the second integral goes from the x value at the intersection point, which is 2, to the x value at the end here, which is 5. And again, I'll have something dx. And then I got to do my top function minus the bottom. So on this first interval from 2 to 5, the top function is the parabola, which is x squared. And then I get minus the bottom function, which was 1. So minus 1. Okay, so in fact, let me write this a little bit closer. So x squared minus 1 dx. I can also move this closer. Plus the integral from 2 to 5. And the top function for that next interval is the slanted line, -x plus 6. And then I got to do minus the bottom function, which is 1 dx. Alrighty, so I actually need 2 integrals for this one. Okay, so from here, evaluating these antiderivatives isn't bad. It shouldn't be, it's just a bunch of reverse power rule. So I'm going to skip that computation and just tell you what you get at the end. So that ends up being 35/6. All right, so I also want to talk about how to do this one other way. So I'll call this solution 2, using a dy integral. Okay. with a dy integral, my area formula is an integral from some number c to some number d, and I do the right function minus the left function. So I need to isolate x when I do this. So x sub right minus x sub left, and I'll have dy. Okay, so let's go back to my picture and think about, well, what will the right function be and what will the left function be. So I'm going to erase this vertical line I had drawn, thinking about it as a dx integral. So as a dy integral, I can see that the smallest y ever gets is 1. The biggest y ever gets is 4. And on that whole range of y values from 1 up to 4, there's one right function. The right function is the slanted line. Okay, so in the slanted line equation, which was x plus y equals 6, this is the right function. This is the right function. If I isolate x, we get x equals 6 minus y, and that's what x sub right is. It is 6 minus y. And then I have to do minus whatever x sub left is. So the left curve is the parabola. So let me write that one underneath here. So the left curve is going to be the parabola, so which was y equals x squared. And let's isolate the x. If we square root both sides, we get x equals plus or minus square root of y. Okay, so let's graph both of those to see what they look like. If I have x equals positive square root of y, when you take the square root of a number, it's not going to be negative. So in this equation, x is always not going to be negative, which means we're talking about just the right-hand side of the parabola, where the x values are always non-negative. All right, so I'm scooting that over to give myself a little bit more room for future videos. Okay, so now let's do x equals negative square root of y for reference. So x equals negative square root of y. Now all the x values are not going to be positive. So this is the left-hand side of this parabola. So what's the equation for the part of the parabola that I care about? So for the part that I care about, it is the right-hand side of this parabola, and that is x equals y. That is this one over here. So that's my left function. This is the left function. So I'll get minus root y. So the advantage of doing this one as a dy integral is I just needed one integral to do it. As a dx integral, I needed to split it up into two regions. Okay, so from here, I am ready to take an antiderivative. That part I'm going to skip. We are ready to take an antiderivative, and once I do, I would plug in the 1, I would plug in the 4, I would subtract those, and if we do that, we can verify. After some computation, we get 35 over 6 in the same way as we did in solution 1. So that's our answer. Alrighty, in the next video, we are going to review Lorenz curves and the Gini index.